All right, so I have four. Oh, I see. Actually, we'll come back to this one. Student holds a meter stick straight out with one or more masses dangling from it. Rank in order from most difficult to least difficult how hard it will be for the student to keep the meter stick from rotating. So here I have a meter stick with several one or more masses on it, and I want to know which one is the most difficult to hold up and which one is the least difficult to hold up, and then order them in that way. You're looking, of course, at the net torque. Which one has the most net torque? Which one has the least net torque? All right, about 10 more seconds. Just guess if you're not sure. I'll stop at 125, 125. Okay, let's see. I think E is right. I'm gonna go ahead and mark it. We'll see. The one that's the hardest to hold up, that is the one with the most torque, is going to be this one because I have the most mass at the biggest radii. In fact, if you wanted to just sort of calculate the relative torque between each of these, we could just say the mass times the moment arm, the length of the moment arm, kind of like you did in lab. Now remember, that's not going to give you the actual torque because the actual torque would be the force times the moment arm. And you'd have to calculate the force for each of these. But the relative torque, this would be 1,000 times 1. This B would be 1,000 times 0.5 or 500. A would be 500 times 1. So notice that even though these have different masses, they have the same torque, and that's because they're at different moment arms. And then down here, D would be 500 times 1 plus 500 times 0.5, which is 250. So my order then will be first C, then D, and then A and B are equal. So C is greater than D, is greater than A, which is equal to B. It's calculating the torque. That's a lot like what you did in the lab recently. Now rank these. I have a force acting on a bar. This is very similar. Rank these in the order of the torques that are acting on these 5 bars. They all either have 2 newtons or 4 newtons. This 4 Newton force is at 45 degrees. All right, let's say about 10 more seconds. I'll stop at 140, 140. All right, let's see. I think A is right. You can get rid of some options here. First of all, we know that one of these provides 0 torque. That's option C. the torque here is 0 because this angle is 180 degrees and the sine of 180 is 0. So C is the smallest. Now notice they all have C as the smallest, but we can get rid of B because it says that the torque due to the torque of bar B is equal to the torque on bar C. Um, then we can pick out which one is our biggest. Figure the biggest one is either going to be this one or this one. It's just a matter of, is the sine of 45 degrees bigger or smaller than 1/2? Sine of 45 is 0.7 or root 2 over 2, so it is bigger than 1/2. So the torque due to E is going to be bigger than the torque D. Remember, this goes back to our torque is RF sine theta. That is the definition of the magnitude of a cross product. So the torque here is going to be 1 meter. Let's say it doesn't give the distance. We'll just say it's 1 meter times 4 newtons times the sine of 45. And that's bigger than 2 newton meters, which would be here, 4 newtons times 1/2 a meter. All right, so that gives us E is the biggest. That gets rid of C and D. And then it's a matter of, what is it, A or E? Um, well, we can look at A. It says that torque A is equal to torque D, and that is true. That I have half the force at twice the distance is going to equal to the torque due to this one. So we can just, by eliminating certain ones, we can say that A is the correct answer. I would expect a ranking problem like that, a couple of ranking problems. We'll see some for moments of inertia too, which we'll get to today. Rigid body is in equilibrium. What are the criterion for rigid body being in equilibrium? The net force, the net torque equal to 0, either 1 or 2, either 1 or 2, or both 1 and 2. All right, just about 10 more seconds. I'll stop at 40, 40. Okay, E is the right answer. Remember, this is like the seesaw problem. In order for a body to be in equilibrium, that means that it's neither accelerating nor is it accelerating in a linear sense, or is it accelerating in a rotational sense for it to be in equilibrium. Now it can be moving, right? It can be moving in a constant velocity or at a constant angular velocity, but it must not be accelerating to be in equilibrium. Often equilibrium problems, it's not moving at all. That's a specific type of equilibrium problem called a statics problem. Um, but in both cases, both the net force and the net torque have to equal 0. We'll see that in the next chapter. And as I said, you engineering students, you'll see a whole semester, actually a whole year of courses in that, and maybe more if you go on in a particular field of engineering. All right, we'll come back to this, and give me just a minute. I want to reorder these so I don't forget that problem. Sorry, give me just a second. All right. Okay. So now we're getting into the kinetic energy of rotation. We're really going to use this to launch off into moment of inertia, because we'll develop our idea of moment of inertia based on the kinetic energy of a rotating body. And then we'll get into some volume integrals today, and I'll give you a piece of your exam. You're going to have actually a couple pieces that'll be take home, so I'll give you that first piece today. All right, so remember we've been making these transitions from linear to angular quantities. Now before we had x, now we have theta. Before we had v, now we have omega. Before we had a, now we have alpha. Before we had force, and now we have torque. We're going to see a couple other things now as well. We'll see that we have both kinetic energy in a linear sense. We'll also have a rotational kinetic energy. And then wrapped up in that, we'll see that we have mass, which measures our inertia, and we'll also have I, which will be our moment of inertia. So this is going to be called our moment of inertia. And today we'll be deriving expressions for moments of inertia. That should be inertia with an R in it. All right. So if you remember, our kinetic energy was 1/2 mv squared. So we can think of a body that's made up of a bunch of different elements. So let's say that we have a disk. All right, we have a disk. It's rotating about this direction, and we can break it up into a bunch of little pieces. So I'm going to break it up into little pieces. These are called differential elements. Right? When we think of this, when we're breaking something up into small pieces, you do this a lot in integral calculus. We call that a differential element or an infinitesimal piece of our object. These are all going to have a mass, dm. They're also all going to have a certain velocity. So if I think of this, I'm just picking out one little piece, but this whole disk is broken up into little bitty pieces. This has a certain mass dm, just like all the other differential elements. It also has a certain velocity. Now, how does the velocity here compare to the velocity of other points on the disk? Is it the same or is it different? Does it have the same or a different velocity from other points on the disk? A linear velocity. Right, they're going to have all different velocities unless they happen to be at the same radius. But remember, for a rigid body, uh, even though the linear velocity of different points is different, but the angular velocity is all going to be the same. That's how we define a rigid body. So this object, even though it has a different linear velocity, it has a constant angular velocity. So it has a different linear velocity, but the same angular velocity. I'll write this out for here actually, but the same omega. Just because the way that we define what is the what is I'm sorry, I don't remember what I was going to say, but they have the same angular velocity but different linear velocities. So our kinetic energy is 1/2 mv squared. I know that v is equal to omega times r. That's just how we relate our linear velocity to our angular velocity. So I can plug that in here and I get the kinetic energy is 1/2 m omega squared r. So this would be like the kinetic energy of my differential element. It's the kinetic energy of that little bitty piece. Um, Now, if I want to know the, yeah, Ainsley? Oh, I should square it. You're right. And that whole thing, that 1/2 m omega squared r squared, is the kinetic energy of our differential element. So I can think of every little piece in that wheel having a kinetic energy that's equal to that value. Uh, that will vary with the radius. Now the angular velocity is constant, so I can find the total kinetic energy by taking, by removing that omega. So my total kinetic energy will look like this. It'll be 1/2 times the sum from I equal 1 to infinity. of my differential elements, mi ri squared times omega squared. So what I'm doing here is I'm saying I have this big disk. It's broken up into little bitty pieces. Each of these little bitty pieces, they all have the same omega. Right? However, they have a mass, mi, and a radius, ri. Those are going to change. Actually, the mass of each differential element will be the same, but the radius will all be the same. So I can take the sum of all those adding up mr squared for each little piece of this disk. If I break it up into a billion little pieces and then add them all up together, then I'll get the total kinetic energy. Now this thing we call the moment of inertia. This sum mr squared is the moment of inertia. And it's a lot like the inertia that we used in linear motion. So in linear motion, we use the mass to describe the inertia. And just remember, our inertia, our mass, described how easily it was to get something to move. So if something had a lot of mass, it was very difficult to get it to move. If it just had a little bit of mass, it was very easy to get it to move. That's, in essence, our definition of what inertia is, and it's measured by the amount of mass. So for angular motion, in a similar way, the moment of inertia, this describes the inertia of the rotating body. So the moment of inertia describes how difficult it is to change the rotational motion of the object. So whereas before, let's go back up here for a second. This looks like a lot like our kinetic energy. Remember we had kinetic energy was 1/2 mv squared. Now we're going to have kinetic energy or equal to 1/2 I. That will be our moment of inertia times omega squared. So we're going to use this definition right here to describe the moment of inertia. Our moment of inertia is going to be the sum of mr squared for a set of discrete particles. All right, so I then is going to be the sum of mr squared. I'm going to have I equal 1 to infinity. That just says that I'm breaking my little disk up into an infinite number of pieces, an infinitesimally small piece. Uh, each of them will have a mass, mi. Each of them will have a radius, ri. Now I'm going to say that the differential element of my moment of inertia is equal to r squared dm. So each little dm has a radius, r. So here's my disk again. There's my dm. That's my mass differential element. And it has a radius, r. You're sort of familiar with this language? I've used differential elements and what have you in Calc 1. You should have, no, not yet. Well, you will in Calc 2 for sure. You should have in Calc 1 when you talk about derivatives, because like when you're talking about dt, when you let this sort of sinking in a little bit. Okay. Uh, all right. So now we can rewrite our moment of inertia, I. If di is equal to r squared dm, we just take the integral of both sides, and then that gives us our expression for I, which is I is equal to the integral of r squared dm. So this is our definition of the moment of inertia. We might also see it just as the sum of mr squared if we're just dealing with discrete particles. Because really an integral is just a summation, but you're just summing up an infinite number of things. Okay? The units for moment of inertia, nothing fancy, it's just kilogram meter squared. And so then our kinetic energy, I've already written this, but the kinetic energy of rotation, or rotational kinetic energy, is 1/2 I omega squared. So remember our equations, as we're making those translations, we had theta equals omega naught t plus 1/2 alpha t squared. We had omega equals omega naught plus alpha t. Those were our two kinematics equations. And then we're going to see Newton's second law is torque. Actually, let me write that for just a second. Now we have our kinetic energy. It's not 1/2 mv squared, but 1/2 I omega squared. And our, we'll see Newton's second law. I'll go and write it here, where our torque is akin to our force, which is going to be I times alpha. So whereas before we had F equals ma, now we'll have torque equals I alpha. All right, let's look at how to calculate the moments of inertia. It's kind of fun. You'll have a take-home portion where you have to derive the moment of inertia for a rigid body. I'm going to do it for you in class, so it should be pretty much a no-brainer. I just want you to put your pen to the paper and just write it out once and write in words what it means. But it'll be worth 5 points on your test. But it should be a gimme, just repeating what we've done here in class. But let's first look at a set of discrete particles. So remember, our moment of inertia is the integral of r squared dm. But we can also write this when we're talking just about discrete particles as just the sum of mr squared. These are basically the same thing, whereas this is talking about a differential element that you're integrating over some body, which we'll do in just a few minutes. This is talking about a set of discrete particles. You'll need to know how to do both for the test coming up in a few weeks. So here I have a set of discrete particles. We consider these to be point masses. I know they're drawn kind of big, but that's just to show that they have different masses. But we consider these to be point masses. And so if I want to find the moment of inertia, I find mr squared for the first one. I will be the sum of mr squared. That's going to be 3 kilograms times 1 meter squared plus 1 kilogram times 2 meters squared plus 2 kilograms times 3 meters squared. So that's, what's that, 3 plus 4 plus 2 times 9 is 18. 7 plus 18, 25. So the moment of inertia for this body is 25 kilogram meters squared. Again, you're really just doing an integral here, except you only have 3 mass elements that you're adding up. You have just the 3 kilogram, the 1 kilogram, and the 2 kilogram, and then you just do that summation. Now, if we look at a rigid body, we can use calculus. We use integral calculus to calculate the moment of inertia for other objects. We're just going to solve this integral. That I is the integral of r squared dm. This was the easiest, the thin hoop. I have a hoop that has a radius r, and it rotates about this axis. This is my axis of rotation. We'll see this in just a bit, but the axis of rotation can change your moment of inertia a lot. Uh, so, for example, we talked about axes of rotation and how it's easier to rotate about certain axes than others. Right, so for example, a human, we can rotate about this axis really easily, but we can't rotate about this axis. I mean, some of us can, but not very many of us can rotate about this axis or this axis. And the reason for that is that our moment of inertia is a lot bigger if we're rotating about these axes than if we're rotating about this axis. Can you imagine why that is? Why is our moment of inertia, our shape hasn't changed, but why is our moment of inertia different if we rotate about this axis than if we rotate about this axis? Just think about it for a few seconds. And remember, our definition of moment of inertia is r squared m, the sum of mr squared. So why would it be more difficult to rotate about this axis than it is to rotate about this axis, even though it's the same body? It is more difficult. It's a lot more difficult to rotate about this axis. That's exactly right. So our moment of inertia about this axis is a lot bigger. So it's just harder to move about this axis because our inertia is bigger. And the reason our moment of inertia, as Cody said, is bigger is because I have mass at bigger radii when I'm going about this axis. Whereas when I'm going about this axis, my radius is just like, 10, 15, 20 centimeters. So I have most of my mass located at very small radii. That's why it's really difficult to do a flip or a somersault or cartwheel or whatever, because your moment of inertia is a lot bigger. All right. So if I have this hoop, my I can divide it up into little bitty mass elements. So this is my first mass element, my second mass element, my third mass element, and then I can break it up into a bunch of other mass elements. In fact, I'm going to break it up into an infinite number of mass elements that are little bitty mass elements. Each of those has the same radius, so the hoop, it turns out, will be really simple to derive the moment of inertia because R doesn't change, or rather, your R doesn't change with M. So DI, I know that DI is equal to R squared dm. This is our definition, and I then is going to be equal to the integral of R squared dm. But because R doesn't change, with M, or with dm rather, that is because all the dm's, all of our mass elements have the exact same radius, I just pull that R out. So my moment of inertia then will equal to uh, R squared times the integral of dm. And then dm is just m. So I then for this, if I integrate from 0 to big M, my I will be equal to m R squared. So my moment of inertia for a hoop is really simple. It's simple because that integral is very easy to do, and that integral is easy to do because R doesn't change with mass, because all the little mass elements have exactly the same radius. That's not always true. In fact, it's often not true. But with the hoop, it's really simple. So when I'm adding up things, I don't have to worry about R changing. Go with me? Yes? You don't look very excited about this, but it's kind of cool. Like I remember integrals being very differential calculus. I really hated a lot because I didn't really understand what was going on. But integral calculus I found to be a whole lot more interesting. Hopefully y'all will find that too. I guess Cody, you're the only one that's had it. Did you like integral calculus better than differential? Yeah. And we'll just do simple integrals. So, I mean, a lot of the stuff that y'all did in calculus, so we're not going to do it all. All right, so let's look now at a rod, a uniform thin rod rotating about its middle point. So this is like you doing a cartwheel about your belly button. The first thing we want to do is define what our mass elements are. So my mass element here is dm. It's located at a distance x from the axis of rotation. So I'm just defining what is my mass element, and it has a width dx. So I start with a definition that di is equal to r squared dm. Uh, this r is actually going to be an x because I'm just dealing with something along a straight line. So I'm just going to let my r be x because it's a 1D problem and it's not I'm not dealing with, things in a circle. So I then, if I integrate both sides, will be the integral of x squared dm. All right. So now I need to define dm in terms of x. And this will be sort of the first crucial step. This one's a little bit harder than the previous one, but it's easier than the ones that we'll see next. So I need to define dm in terms of x. So dm then will be, I look up here, I have a rod of mass m and of length L. So dm will be m over L times dx. Because it has a width, that mass element has a width dx. If I multiply it times the mass over the length and multiply it times the width dx, that'll give me the mass of that mass element. But now it's written in terms of x instead of m. This is often called the linear mass density. It's similar to volume density, except it's a mass per unit length. This is usually given the Greek letter lambda as the variable that describes it. So the linear mass density, some of you engineering students, you'll probably see that later when you get into your upper level courses again. All right, so that's our linear mass density. Now I can rewrite that. I have I as the x squared, and now I put in my expression for dm, m over L times dx. M over L, this is the mass of the rod, this is the length of the rod. That does not change with x. So I can take that out of the integral. They're just numbers. I can take them out, they don't change. And so I'm left with m over L, integral of x squared dx. And then I'm going to integrate this from negative L over 2 to L over 2. That was based on how I defined the length of the rod. You might have different limits of integration, but it's easier in this case if you go from negative L over 2 to L over 2. All right, y'all can do that integral. What's the integral of x squared x dx? Right, not 2x, you're thinking derivative, but I add 1 to the exponent, and then I divide by that number. So it's going to be x to the 2 plus 1 over 2 plus 1. This would be m over L, x to the 2 plus 1 over 2 plus 1. I also have to integrate, I have to evaluate it at my limits of integration, negative L over 2 to L over 2. So this is going to be m over 3L. I take that 2 plus 1 out of, move it out of there, x to the third, L over 2, negative L over 2. I can evaluate those. It's going to be L cubed over 2 cubed, which is what, 8, minus L cubed over 2 cubed, which is 8. So this is actually a negative, so those go positive. So that is m over 3L 2 times L cubed over 8, which is L cubed over 4. And then that gives us our expression, which is going to be 1/12 ml squared. Okay, so this is the moment of inertia for a rotating bar. That is a bar that's rotating about an axis that's through its center. If you had this rotate about a different axis, say around the end of the bar, it would work out differently. But you can imagine it would still work out the same way, in fact, quite a lot the same way as it does here, if I let it rotate instead by an axis that is here. You'd set your limits of integration then not from negative L over 2 to plus L over 2, but from 0 to L. We're not going to do that here, but you can imagine that it would change, but it would still work out much the same way. All right. Actually, yeah, why don't we do that as our take home? Let me think about it. I'll think about it. I'll let you know. Okay. Um, Now we can also do integration of a solid cylinder rotating about its central axis. So you'll see this a lot come up in some of your problems where you have a cylinder that rotates about an axis. That's going to be the same as like a disk. So if you have a solid cylinder, you can also think of this as a disk. A disk is just a really flat cylinder. So if you ever see a disk like a merry-go-round or a spinning disk or a flywheel, those are all solid cylinders. Uh, In this case, you want to think about what your differential element is. We're going to let our differential element be an annular cylinder. You know what an annular cylinder is? An annular cylinder is like you know the roll that you have left over, the cardboard tube when your paper towels are gone? That's an annular cylinder. It's a cylinder that's hollow in the middle, an annular cylinder. You follow me? So we're going to let our differential element be an annular cylinder whose mass is dm. So it's going to be this object right here. If you look from the top of this solid cylinder, that's going to be our differential element. Um, the moment, or rather the density of this annular cylinder is m over v, which is going to be m over pi r squared. Or excuse me, it should be a big R, pi r squared times L. So the density of this cylinder, of the big cylinder, is just the mass over the volume. This is the volume of our big cylinder, pi r squared L. We'll use this in just a bit because it'll come up again. We apply our definition for the moment of inertia. di is r squared dm. And then we integrate both sides. So I is r squared, the integral of r squared dm. We always start with that. We start with our definition of the moment of inertia. And then we have to define what is the mass of our differential element. So if we think about our annular cylinder, it has a mass here equal to the circumference of the cylinder times the length of the cylinder, or the height of the cylinder, times the width of it, which is this width, times the density. So these three values give you our volume. I multiply this times this times this to give us the volume of the annular cylinder is equal to the circumference, that's 2 pi r, times the height, that's L in this case, times the width of our annulus. And that gives us just the volume. And we multiply that volume times the density, then it gives us the volume of the annular cylinder. All right? And then when when we multiply that times the density, it gives us the mass of dm. So it's a little trickier here to define dm, but if we choose our um, our differential element correctly, then it becomes easy. Now there are other differential elements that you could take here. Like I could just take a little point like I did with the hoop, and then I would have to define the position of that based on the radius and the angle, and it gets kind of messy. You could also do, gosh, what else could you do? I think that's about it. This is really the best differential element that you could do. All right. When y'all get into calculus, I think this might be Calc 3 actually, when you get into volume integrals. Is that right? When y'all get into Calc 3. Chem majors, you take Calc 3? You do, right? No, you don't. But you engineering majors will. And some of you even do this a lot when you go into your upper level classes. Okay. All right. So that's what we're doing here, volume integrals. So now we define our dm. Our dm is 2 pi r. That's the circumference of our differential element times the height times the width times the density. Now I can put that in. I get it's the integral of actually, I'm going to go ahead and write this a little simpler. Let's pull some stuff out. I'm going to pull out 2 pi L and rho and the integral of r cubed dr. What I'm doing here is I'm taking this dm and I'm plugging it in right here for dm, but then I'm pulling some stuff out that doesn't change with r. 2 pi doesn't change, L doesn't change, and rho doesn't change. But now I have a nice integral that I can evaluate because I have a variable that changes with the differential element. And this is going to be from 0 to big R. Uh, the integral of this is 2 pi L rho, what's it going to be? R to the what? Right, R to the 4th over 4. I evaluate that from 0 to R, and I get my expression, which is going to be 2 pi L rho R to the 4th over 4. I can still simplify this a little bit more because remember our density is equal to this, m over pi r squared L. So I can have 2 pi L mass over pi r squared L times r to the 4th over 4. I get some things canceling out here. Pi's cancel, L's cancel. A 2 cancels here and leaves a 2, and an r squared here and leaves an r squared. And so my final answer is 1/2 mr squared. That's how I find the moment of inertia of a solid cylinder. It's a little more difficult than the disc, or it's definitely more difficult than the hoop, a little more difficult than the bar. But the trick is using that annular cylinder to get your differential element correct. All right. Um, I'll send you guys an email about what to do for the take-home portion of this, but it'll be something like one of these derivatives. I'll let you know. All these derivatives are online. I might give you a slight variation of one, but I'll make it clear in the email. I'll send it out later today or so. Okay? We can do it for all the others. These are just some of the shapes. We're not going to go through all of them just to belabor it, but you can do that similar process for all sorts of different things. We did the cylinder of radius r and the thin rod of length b, but you can do it for a cylinder of radius r where you're rotating about an axis through the middle, and then you can also do it for a solid sphere and a thin-walled sphere. Let's finish up those clicker questions. So I don't like usually to do a whole lot of derivations, but I do want you to be able to do it for the exam, so I wanted to use some class time for that. Done these. All right, so I have two spheres. They have the same radius and equal masses. One is made of solid aluminum, and the other is made from a hollow shell of gold. Which one has the bigger moment of inertia about an axis through its center? Which of these, they have the same mass, but since one is aluminum, which is lower density than gold, uh, it's solid, whereas the gold one is hollow. Which one has the bigger moment of inertia? All right, I'll stop at 1 minute. It's 5 more seconds, a few more seconds. Okay, let's see. So most of you put B. B is right. In fact, if we go back and look at that table, these are our two spheres, and we can see that having the same radius and the same mass, I have two different spheres. One's a solid sphere, and one's a thin-walled sphere. And see, the moments of inertia are similar except for the coefficient. This is 2/5 and this is 2/3. So the one with the bigger coefficient will have the bigger moment of inertia. Which is bigger, 2/5 or 2/3? Right, a third is a lot bigger than a fifth, so 2/3 is bigger than 2/5. So the thin-walled hollow sphere, which was the gold one, will have the bigger moment of inertia. But don't think about it in terms of the equation. Think about it in terms of our basic definition of moment of inertia. That is that I is equal to mr squared, or the sum of mr squared. The one that has more mass at bigger radii is the one that has the bigger moment of inertia. And the gold sphere, which is hollow, has all of its mass out at big radii, whereas the aluminum sphere, which is solid, has its mass distributed over all radii. So the gold sphere will have a much larger moment of inertia because it has that mass spread out over, or has that mass concentrated at, at big radii. So the gold one is correct. Here I have 3 or 4 configurations, and I want you to rank them from lowest moment of inertia to highest moment of inertia. Now they all rotate about the same axis, or they rotate rather about an axis shown by the dashed line. But all 4 shapes are exactly the same. They consist of one bar teed in with another bar, 2 identical bars that are connected uh, at the midpoint of one of the bars, so it makes a T. So now rank these from the order of largest moment of inertia to smallest moment of inertia. And you always want to think about how does this, the sum of mr squared, which of these has more mass located at larger radii? Which has more mass located at larger radii? And that one will have the biggest moment of inertia. All right, I'll stop at 130, 130, or I'll go to 132. Just guess if you're not sure. All right, D looks good, I think. Let's see. We'll step through it. I'm not sure I think that is right, but let's just step through it. So uh, it looks to me like A has the most mass at biggest radii, because A has this one rod that's all the way out as far away as it can get from the axis of rotation. And then it also has this rod, which has its mass distributed over different radii. But that one big rod out at the maximum radius, none of the other objects have it. So I'm pretty sure that A is going to be the biggest. So I can get rid of this option, and leave these other 2. Now let's see, option C here has the moment of inertia A equal to the moment of inertia of C, or of B rather. That's not the case because I have my axis of rotation here that goes through that bar, whereas for A, it's in a completely different position. In fact, uh, B is going to have a bigger or smaller moment of inertia than A. Quite a bit smaller, right? Because the moment of inertia due to this bar will be 0. It has 0 contribution because of this mr squared. R is equal to 0 for that one. So I can get rid of C. So now that leaves me with either D or E. So A is the biggest. I can also say that C is the smallest. C is the smallest because it has the axis of rotation going the through one of the bars, so that moment of inertia just goes away basically. And it's smaller than B because here my bar just goes out to a distance of r over 2. It splits the difference on that bar. Whereas with B, uh, this goes over a distance equal to r, from 0 to r. All right, so C is going to be the smallest. And then the question comes out, well, is B bigger than D or is B smaller than D? um, B is going to be smaller than D. So D will be my next one, and then B. So what was it, from biggest to smallest? I'll put D. Yeah, D is right. So the first, this one has the biggest moment of inertia. It has the most mass at biggest radii. This one has the smallest moment of inertia. It has the least mass at smallest radii. And then these two come up. Um, this one is basically identical to this one, except for this bar that's jutting out. So this one has a bigger moment of inertia than B, which gives us D is the right answer. If you look back at some of the old tests, you'll see some similar questions. Make sure you look at those that you're okay on this, because you'll certainly see a question where you have to rank moments of inertia. Once you do it a few times, don't sweat it. It sort of becomes more intuitive that you can sort of think about where those masses are located. All right, we'll come back to this. In fact, I think we're out of time, so we'll just wrap up there. We still have a couple more things in this chapter. Wednesday, we might start moving into the next chapter on equilibrium. Probably not. We'll probably just finish this chapter up on Wednesday. Have a good day, though, okay?